Welcome friends. Today we will discuss part 1 of lecture 3 in which we will study isomerism in monosaccharides. So first of all, what is an isomer? Isomers are different compounds with same molecular formula but different chemical structure. So those compounds which have the same molecular formula but different chemical structures are known as isomer. And the phenomena of having isomer is known as isomerism. The most important types of isomers are stereoisomers, which have the same molecular formula but with different arrangement of atoms in space. So the formula may be same, but their arrangement of atoms is different in space. In figure 1, you can see glucose and fructose are given, which are isomers of each other because they have the same molecular formula C6H12O6, but their chemical structure and arrangement of atoms in space are different. So you can see here in C1 and fructose, the A is fructose. Here in C1, CH2OH group is present, and glucose at carbon number 1 and aldehyde group is present. And fructose and carbon number 2 ketone group is present, and in glucose H and OH group is present. So although they have the same molecular formula, but their arrangement of atom or structure is different. So they are also isomer and stereoisomers of each other. Then how isomers formed? Isomers formed or occurs due to the presence of chiral carbon. So chiral carbons are those carbons which are attached to 4 different groups and is represented by 2n, where n is equal to numbers of chiral carbons. So how isomers forms? Isomers form due to the presence of chiral carbons. In glyceraldehyde, which is a reference molecule, 1 chiral carbon is present, so it is 2 raised to the power 1. So they have 2 isomers, and glucose contains 4 chiral carbons, which is equal to 2 into 4. So it has 16 isomers. So glyceraldehyde have 1 chiral carbons and have 2 isomers, and glucose have 4 chiral carbons and thus have 16 isomers. In this figure, 2 chiral carbons and glyceraldehyde and glucose is given. This A is glyceraldehyde. So you can see this is carbon 1, this is carbon 2, this is carbon 3. So only this carbon 2 is attached to 4 different groups. So this carbon is a chiral carbon. So glyceraldehyde have 2 isomers. Then B, this is the structure of glucose. You can see here glucose have 6 carbon. This is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So in glucose, carbon 2, carbon 3, carbon 4, carbon 5, they are chiral carbons because they are attached to 4 different groups. So in glucose, 4 chiral carbons are present and 16 isomers are possible of glucose. Next is the types of isomerism. First of all, we will discuss about the epimers. Epimers are those isomers which are formed due to variations in configurations of OH and H group on specific carbons atom other than anomeric carbons. So what is anomeric carbon? Anomeric carbon have specific functional group. For example, in aldoses, they have aldehyde functional group in carbon 1. So the anomeric carbon in aldoses is C1. In ketoses, which have ketone functional group, the anomeric carbon is carbon 2. So epimers are those isomers which have variation in configuration of H and OH group on specific carbons. For example, glucose have mannose and galactose epimers. They are formed by the epimerization at carbon 2 and 4 by the group of enzymes known as epimerases. So epimerases are the enzymes responsible for the epimerization of glucose. So glucose, you can see here in figure 3 structure of glucose epimers. This is D-glucose. You can see the structure of glucose here. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So the epimers of glucose known as mannose and galactose are, they have the difference in configuration of H and OH at carbon 2 in mannose. You can see here the carbon 2 configuration in glucose. They have OH at the right side and H at the left side, but in mannose have hydrogen group at the right side and OH group at the left side. So mannose is the epimer of glucose. Next is galactose. Galactose have difference in configuration of H and OH group at carbon 4. So you can see here in glucose, the configuration of H and OH at carbon 4 is here. They have OH at the right side and H group at the left side. But in galactose have hydrogen group at the right side and OH group at the OH group at the left side. So mannose and galactose are the epimers of glucose. Next one is the ketose and aldose isomerism. This type of isomerism exists on the basis of functional group. For example, fructose and glucose. We will discuss fructose and glucose as an example. In glucose, the functional group is aldehyde group at carbon 1, which is also known as aldohexoses, because aldo means it have aldehyde functional group and hexose, it has 6 carbon. Next is fructose. Fructose have a keto group at carbon 2, also known as ketohexose, because it have ketone functional group and it is hexose, it has 6 carbon. So at figure 4, aldose and ketose isomerism is given. This is glucose, and you can see in glucose the functional group is aldose, that it has aldehyde functional group, and this is fructose, and in fructose you can see at carbon number 2 a ketone group is present, so it is ketohexose, because both have 6 carbon but the functional groups are different. Glucose have aldehyde functional group and fructose have ketone functional group. So this is aldose ketose isomerism. Next type is pyranose and furanose ring structures. Monosaccharides are found in either pyran, a 6-member ring, or furan ring, a 5-member ring. So in solution, glucose occur more than 99% in the pyranose form. So in this type, the monosaccharides can either be found in pyran or furan ring structure. The rings form of D-glucose are represented as alpha D-glucopyranose and beta D-glucofuranose. In figure 5, the structure of glucose both in pyranose and furanose forms are given. You can see this one is a pyran group. We already discussed that pyran group is a 6-member ring structure which have 5 carbon. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, and this is carbon 5. So pyran have 5 carbons, but it have 6 members. So oxygen is another member, so it is 6-member ring which have 5 carbon. This one is furan. Furan is 5-member ring. This is 1 member, this is 2nd, this is 3rd, this is 4th, this is 5th, but they have 4 carbon. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. So monosaccharides exist either in pyran group or furan group, but most commonly they occurs in pyran group. This is the example of alpha D-glucopyranose. You can see here the 6-member ring. This is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5, and the carbon number 6 is outside the ring. So the ring contains 5 carbon and 6 members, including oxygen. Alpha and the alpha, we will discuss the alpha and beta in the next form of isomerism. This is uh, alpha D glucofuranose. So you can see here furanose, we know that it have 5 carbon and 4 carbon and 5 member ring. So this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, and carbon number 5 and 6 are outside of the ring. So the ring contains 4 carbon, and including oxygen, it have 5 member ring which have 4 carbon. So this is the another type of isomerism. The next type of isomer which is found in monosaccharides are known as anomers. Anomers are those isomers that differ in configuration around the anomeric carbon. What is anomeric carbon? Anomeric carbon contains a specific functional group. C1 is the anomeric carbon in aldoses as it contains aldehyde group at carbon number 1, and C2 carbon is the anomeric carbon in ketoses because at carbon number 2 it contains ketone group. Next is the reaction between the aldehyde group at C1 carbon and OH group at C5 carbon form a hemiacetal linkage. This type of linkage in ketoses is known as hemiketal linkage, and it is formed between carbon 2 and carbon 5 because we know that in ketoses carbon 2 is the anomeric carbon. Next is the example of D-glucose. It exists in solution in 38% as alpha glucopyranose form and in 62% beta glucopyranose form, and less than 0.3% is present in alpha and beta anomers of glucofuranose form. So these type of isomers interchange between one another. This interconversion of alpha and beta anomers of D-glucose in aqueous solution is known as mutarotation. In figure 6, the representation of alpha and beta anomers is shown in Fischer projection and Hayward projection. And you can see here now A is Fischer projection in straight chain form. This is the normal structure of D-glucose. Here an hemiacetal linkage will be formed between carbon 1 and carbon 5, which will result into two isomers known as alpha D-glucose and beta D-glucose. And alpha D-glucose, a hemiacetal linkage is formed between C1 and C5. And you can see here the position of OH and H group is different than in beta form. Here the OH group is found on the right side and H group is found at the left side. And beta D-glucose, H group is found at the right side and OH group is found at the left side. So these are the alpha and beta D-glucose form. Next is the Hayward projection. This is the normal D-glucose. Here you can see this is carbon 5, this is carbon 1. The hemiacetal linkage is formed. So this is the alpha D-glucopyranose. Here the OH group present at the right side will be present on the lower side, and the H present on the left side will be present on the upper side. This is alpha D-glucopyranose. And beta D-glucopyranose, this is carbon number 1. The H group is present on the lower side and the OH group is present on the upper side. So these are the alpha and beta anomers. This is also shown in figure 7, the anomers, alpha and beta anomers, formation of two cyclic form of D-glucose. It is the reaction between aldehyde group at C1 carbon and OH group at C5 carbon forms a hemiacetal linkage and producing alpha and beta anomers. The interconversion of alpha beta anomers is known as mutarotation. Here you can see here this is the normal structure of glucose. D-glucose, this is C1. The hemiacetal linkage will be found between C1 and C5. So you can see this is the hemiacetal linkage. it results into alpha and beta anomers of D-glucose. So this is the alpha D-glucopyranose. So you can see here the OH is on the left, on the lower side, and H is on the upper side. Here in beta D-glucopyranose, the H group is on the lower side and the OH group is on the upper side. So these are all about different types of isomers and monosaccharides. Thank you for watching. Stay healthy and happy.